Using nanotechnology, scientists in South Korea may have created a breakthrough in cancer treatment.
What's termed nano-robots at this point?
Made in a lab, marching through your body to a tumor and then killing it.
There's all sorts of possible things you might think about people using nanobots for.
What we have gotten interested in is trying to understand how life is put together.
Could these things be weaponized? Yes.
And we could end up creating another Oppenheimer's nightmare.
Who wouldn't want a heart that's comprised of intelligent, tiny things that actually beat?
I mean, it's not crazy. That's not a crazy idea.
We're going to see things no one has ever seen before. Not just something under a microscope. Think about it.
That's the trouble I have. Being shrunk.
In 1966, audiences were asked to suspend their disbelief as they watched a medical crew shrink to particle levels in a submarine that was injected into a human body. In the movie, the crew successfully traveled to the patient's brain and fixed a wound from within. Most called it fantasy, but some asked, what if?
Science fiction writers are inspirational to everybody. They inspire our movie directors and producers. They inspire people who watch those shows. They inspire people who read the books. They inspire scientists too.
Steve Jobs said, you don't know what you like until you see it. Even the simple things like, remember in the original Star Trek, the doors opened automatically.
I think we just made contact, sir.
Well, gosh, those are just everywhere now. So many astronauts and innovators and inventors and engineers were motivated to go into their field because of what they saw on TV.
Film has definitely created a certain idola, I guess you'd say, around robotics. Probably does affect the way even the experts think about what could be done. And certainly it affects the way investors think.
The real-life potential of nanotechnology in applications such as drug delivery and gene therapy often clashes with fictional plot lines.
Nanotechnology.
Where nanobots become a futuristic force for evil.
Michael Crichton wrote this book, Prey. The nanobots acquired swarm intelligence, and they would do things like control your brain, or they would just eat you.
While science fiction often emphasizes the dark side of nanobots, scientists today see hope in the promise of medical nanotechnology, transitioning from science fiction to science fact.
The nanotechnology targets the damaged cells and repairs and regenerates them.
Scientists are now on the verge of creating tools that are so minuscule they can be used to target and cure complex diseases.
Molecule-sized machines which can enter a cell and repair it.
This would be ultimately the ultimate fantastic voyage, going to different locations in the body and really curing faster and better compared to conventional medicine.
Although the science is still new, the progress to reality is moving fast. It is predicted that nanotechnologies will revolutionize our lives within the next 20 years. These discoveries are bringing hope to many, but they are also raising flags and asking questions about ethics, safety, and what it will mean to be human in the future.
One of the great concerns about these technologies that would be used to essentially improve the world somehow, we all agree that the world could be improved, but most people think that that should be a limit.
There's a lot of directions we can go and a lot of variety. As a society, we should decide, how far we want to take this.
We typically do not want to live in a fully synthesized world. We do not want to live in a world where every last thing that we see is the result of human artifice.
The question is whether it's worth it, right, to use this technology versus other things that we already have.
Finding the boundary will be a challenge.
must understand that in the science of nanotechnology, we are dealing with objects which are measured in nanometers. A nanometer is 1/100000th of a meter.
At 10 times smaller than a normal cell, nanobots are tiny self-propelled machines that can be programmed to perform specific tasks.
I like to call like a small submarine, right? So it's like tiny device that when you put it to a fluid, and then it makes this nanobot to move. And can not only move, but can transport things or drugs, can target, can be steer, can drill, right? Can sense.
So how do you build a robot at that scale to do the functions that a robot has to do? Isaac Asimov wrote the iRobot series, and so he defies what he called the 3 laws of robotics.
Yeah, I know, the 3 laws, your perfect circle of protection.
A robot cannot harm a human being.
Asimov's first law was that a robot should not be harmful to people. And that maps pretty much directly to nanorobots, right? You don't want your nanorobot to be toxic.
Initially, gold and platinum were used to create the first nanobots, but these materials proved to be too expensive and were not very biocompatible.
Metals tend to create toxic effects, inflammation in individuals. Take, for example, hip implants. So when hip implants first came out, they were largely metal of different kinds, and they created all kinds of problems, and you started moving to less toxic metals and moving even into polymers. There's a lot of work in the nanobot space on silica.
Any operation in the body, if we want the FDA to approve it for routine use, need to be completely safe and non-toxic.
But doesn't the second law state that a robot has to obey any order given by a human being?
The second law, the robot has to follow its programming, is a little bit more difficult to do in the nanoscale.
Not everything just scales so well down, because it's at some point you can't shrink your circuit board that much anymore.
How do you program a nanoparticle when an individual nanoparticle is smaller than the size of a single transistor, so it can't have a computer built in on board? So how you do that programming is through chemistry. The nanorobot's programming is done by molecules and chemicals that we put on these robots and design so that they will do specific functions like fold up in the right way or attach itself to a diseased tissue or signal that it's present.
The third law states that a robot can defend itself.
Yes, but only when that action does not conflict with the first or second laws.
Asimov's third law is the one where I differ from his model. In the macro scale world, the third law was that the robot must protect itself. In the nanoscale world, when the robot is much smaller than something that you can pick up and turn off easily, a nanoscale robot should not protect itself. In fact, it cannot protect itself. It must self-destruct. It has to go away after it's performed its function. If it's too stable, it'll be there forever. There's risks of these things accumulating, just like asbestos. Most people know asbestos can be quite harmful. Why? Those fibers are actually nanofibers. If those fibers get into your lungs, they're so small that they can get really deep into the lungs, and then they'll stay there for basically years. A lot of times it's not just the composition, the actual elements that are so important, it's how it's put together. It's how stable it is. If we make enough of these materials, we have to consider how we're going to be disposing of them.
Just moving something at the nanoscale is really a challenge.
Once inside the body, getting the nanobots to move requires power. Finding the tools to propel them comes with its own set of obstacles.
How do you build in little wheels or motors into something that's really, really small?
Can you actively propel and then move through the body? Maybe some envision even against the stream. The same propulsion techniques that work well when you're large, when you're a big fish, you don't see the same in nature when you're small.
And if you think about all the engines we use, the internal combustion engine, the steam engine, electric engines, all of these macroscopic engines basically work on physical principles that don't translate to the submicron or nanometer.
One solution is to try to drive them with external forces, such as magnetic fields, ultrasonic sounds or light rays.
A lot of folks in the field, us included, are firm believers that magnetic materials are quite interesting because you can generate forces and torques on them. You can generate forces on them from a distance with externally generated fields. So that's a way you can propel them.
External forces make it easy, modulate the force to move the bots, but it has its downsides.
It's very hard to direct them to hone on to, let's say, a specific cell. It's a lockstep behavior. All the bots follow the external field.
While this may work for steering a single nanobot, like during a surgical procedure, it has weaknesses when trying to control swarms of them.
Each of these warheads contains 7 million nanomites.
Hollywood has shown us scenes of swarms of nanobots throughout our lives. What was once used to drive storylines in film is quickly becoming a reality.
It's unlikely that one nanobot can carry enough drug to treat whatever that needs to be treated.
You need to be able to inject in your body like millions of particles. They will collectively move and attack a disease.
You're always gonna work with a lot of nanobots, right, to have actually an effective result. So you kind of always work with a swarm.
So like a flock of birds, you see these flocks of birds flying around, and you're kind of wondering, how do they all know where to go, right? And how do they keep their distance just right?
These swarms work together to achieve a larger goal that no one individual nanobot could accomplish on its own.
Identical nanobots that communicate with each other, come together, and as a group, they can carry large cargo.
In this scenario, these nanobots would need to be able to propel themselves through a series of chemical reactions.
Since nature uses catalysis to make everything move and nanomotors to make everything move, why can't we do that?
You use glucose as a fuel to move. Use the glucose in your blood to move your nanobot.
Researchers at Penn State and University of Pennsylvania began conducting experiments with nanobots using chemotaxis, the same phenomenon that bacteria use to move themselves and locate nutrients. Imagine a trail of ants following breadcrumbs to reach their destination. These nanobots would behave similarly and follow a chemical trail.
We got together and did this experiment, and right away, these things swam around and looked very much like bacteria swimming in bacterial culture. Then we knew we were onto something pretty interesting.
Because it takes millions of nanobots to perform a single function in the body, scientists are researching quicker ways to assemble them. One solution is using a process called self-assembly. This process doesn't require an assembler, but the nanobots would come together spontaneously.
As chemists, we know how to do that. We mix the right chemicals in a beaker in the right way, heat them to the right temperature, and play other games with them, and they can build certain structures.
Once the structures are created, a level of complexity can be added to create more advanced objects.
There's this term called DNA origami or RNA origami. Origami is taking a piece of paper and folding it up according to a certain plan to make some pretty structure like a swan. It turns out you can do that kind of with molecules, unlike the origami in the macroscopic world where you take one piece of paper and you fold it up. We make thousands or millions, billions of these molecules all in a beaker, and they all have the same exact sequence. So they all fold up on their own spontaneously, and so you make 10 million swans in one step instead of folding one up after the other. And so that's also the beauty of what we refer to in the chemistry world as self-assembly.
You put in the ingredients and you put in the right forces and it gets assembled. There is one example of that, which is us. We assemble ourselves and it's a self-assembly process. There's no one who assembles us. What we have gotten interested in is trying to understand how life is put together.
Self-assembly is a highly debated topic among the nanoscience community. If these particles could assemble themselves if placed in the right ingredients, and if these ingredients can be found in the human body, could nanobots eventually self-replicate and reproduce on their own?
The cat's kind of already out of the bag. There are already tools out there that nature's already developed to make a nanobot replicate that we just try to mimic. One of them is viruses. A virus, its job is to replicate. They evolve and they become efficient because they can get into lots of people and then continue to grow.
China has identified the cause of a mysterious new virus.
This is a rapidly emerging situation.
The Italian government tonight put the entire country on lockdown.
It's a real concern when we're working with biological systems that are relatives of viruses that we don't build a nanobot that's going to be capable of replicating. If it self-replicates and it goes bad, it can just keep going and you won't have a way to control or turn it off.
You are creating not one of something, but millions or billions of something. You don't want to create a technology that you yourself cannot control. So technologies that cannot be recalled are justifiably subject to much higher level of scrutiny.
Control and autonomy need to be considered when we discuss the purpose of nanomedicine, because this type of treatment has both known and unknown implications.
What I could see certainly coming off of this is selling your medical information for private companies doing drug development. That already happens today.
Trackers such as smartwatches, fitness bands, patient portals, and even glucose monitors are already collecting health data and statistics. With a new level of access to the human body, what type of biodata could nanobots collect?
New medication that will track whether a patient is following their prescription.
This is another example of a property issue. Who owns it? And we're not talking about like the CIA having this information about you or the NSA. We're talking about your insurance company.
Another concern around collecting biodata is privacy protection. Without these protections, issues may arise over who can access this information.
There is a catch-22 there, right, which is law enforcement.
A judge is allowing prosecutors to use Fitbit data to prove that a murder suspect is guilty.
Do you really want to be monitored for your entire life? Do you want every last aspect of your existence to be cataloged? Typical notions of freedom don't include the idea of sort of constant surveillance like that.
Most people don't care about whether their data is being collected by somebody. All they want to do is be safe and be fixed.
My dream is sort of to have my doctor, through a bunch of little nanobots in my body, able to monitor me in real time and be able to tell me, hey, Zolt, unfortunately, you got some cancer on your liver, or unfortunately, your heart has been missing some beats. So let's fix that right now.
Part of freedom is to not be monitored like that, even if it does have some good purpose. Where would you draw the line?
As nanotechnology improves, so will our care. Cures, treatments, and effective preventative measures will certainly be available, which leads to new questions.
Is there something wrong with the individual that we need to fix, to remedy, to cure? Or also perhaps preventative. And if one of the things we do to prevent certain things is to render some organ, some system, or that organism more resistant, more resilient, more capable, the question then becomes, at what point does enablement equal enhancement?
And Oscar Pistorius, the greatest Paralympic athlete of all time.
I think nanobots are a further technological evolution of the human species, in which we are increasingly going to have non-organic substances in us that allow us to function more effectively. So what if I could use a nanobot and increase the range of my hearing? We already have cochlear implants for people who are deaf. When does it go from treating a disease state or a dysfunction to a cognitive enhancement?
When you consider the implications, like these things filtering through your body, maybe even replacing cells at some point in the future. I mean, who wouldn't want a heart that's comprised of intelligent, tiny things that actually beats and gets the air in your lungs, as opposed to billions and billions of heart cells that ultimately fail? I mean, 25% of us will die from a heart attack or a heart failure.
If we have more than half of our physiology being affected by implantable devices, when do we go from being human to being something else.
Are you speciating in a way based on our own creative evolution and our financial ability to afford the tech?
Now, we're pretty far away from that still, but I certainly think that could easily be part of a 100 or 200-year future.
Being modified to live longer, have intellectual and physical advantages might sound great, but is it for everyone?
The biggest worry with all of these human enhancement technologies is that they will be available to some and not to others.
Your first many, many years of a new technology is not going to be cheap and is only going to be consumed by people with a lot of money.
If certain people can afford it and others can't, do they have a competitive advantage?
Because we're no longer talking about a little advantage. We're now talking about a possibly massive advantage.
And then also what happens when those who are neurotechnologically enabled are enabled no longer.
Most technologies become obsolete as newer models come to market with enhancements and updated improvements.
Today, Apple is going to reinvent the phone.
If we become a society that relies on nanobots in our bodies to perform, will we need to also rely on endless updates?
If I'm stuck with this old version, and there are things I can't do with it and everyone else can, is that now a disorder?
Should we be using technology to enhance the unfairness of our innate biology? I think that's a very deep question.
When you can think of all the good things that can be done with technology, unfortunately, usually there can also be very bad things that can be done too.
Technological development does not necessarily go to the greatest human need. It more often goes to the interests of those with the power.
Technology meant to find cures and improve our health can create devastating and harmful consequences in the hands of those with nefarious intentions.
I'm really worried about the military applications of this. Could you develop weapons, nano robots, for example, that can go in and invade somebody and kill them? This microscopic thing has gotten into their body.
Could these things be weaponized so as to be able to then be directed against a particular individual based upon that individual's biological, quote, profile? Yes.
This could lead to terrorism applications, crime.
We have to understand that we really do not fully comprehend the full scale or dimensionality of functions, capabilities, and defects that might be manifest at the nanoscale.
If you could have one human act release one set of nanobots that would then change the world, that's a degree of power over the received worlds that many people are concerned about.
In 2004, the United Nations added nanomedicine to the Biological Weapons Convention in order to maintain global public health and safety.
There was real fear that we were unleashing a beast that we could not put back in the box. Are you creating technology and devices that could change the world and we could end up creating another Oppenheimer's nightmare?
I've had talks with the Defense Department, DARPA-type people who have been asking the same question.
Once you create something, you can't destroy that creation. It's understood by humankind from that point forward, and how that technology is going to be implemented and used is really the tricky part.
Are we prepared? Not only if something were to go wrong, but when something goes wrong. What we're reaching here is sort of a paradox, a dilemma, the Collingridge dilemma, if you will, which is basically we won't know unless we go. And that's absolutely true.
I think it's a revolutionary time that we're living in. There are going to be ethical questions, but as a society, we've dealt with similar issues before.
He says he genetically edited human embryos.
A line has been crossed that should not have been crossed.
It's very disturbing.
Anything that we talked about here has a utopian side, and the flip side of that coin can be dystopian. And they're both real. The public should become much more aware of what the real science and technology is.
I don't think that nanotechnology is going to reach the state that some of the wilder projections give. Once we become more accustomed to them, people will be less afraid of nanotechnology.
They'll be scared at first, but once they see what the technology can do, I think that they will embrace it.
There's been a big shift in how we think about nanomedicine and nanotechnology and nanorobots. Now the community is starting to say, wow, these work really well. What are the other things we can do?
Globally, researchers are working on these challenges. To date, over $70 billion is spent annually on nanobot research and development, with nearly 24,000 patents worldwide. The key driver in the field continues to be biomedicine.
Ultimately, science is about curiosity. I tell my students that, most of the time you are going to fail. But when you find something, it's wonderful. And if that helps other people, that's even better.
We've already come a long way, but there's a long way to go. And nature continues to be an inspiration. As we learn how nature pulls these things off, we can think about engineering systems that do that.
Inspiration may come from nature, science fiction, or Hollywood, but the desire to discover newer and better possibilities remains the motivational force.
If you look back at the fantastic Voyage, but it was all about swallowing the surgeon. This was science fiction 1966, almost 55 years ago. So the progress has been amazing, and there are more and more groups around the globe. It's still a bright future, a lot to do, but a lot of possibilities.
Generally, I'm optimistic. It's a technology that we're just starting to touch, and so far it looks like some potentially positive use cases are arising.
People have been skeptical of radical science anytime they see it for the first time, but they were skeptical when somebody created fire and controlled it for the very first time.
There are many people who do not trust elites in general and scientists in particular. These people will be very skeptical of nanotechnology.
We're going to want and need this technology in the future. It's going to make our lives better. So I always tell the naysayers, hey, just stick around and watch, and you'll probably join us too sometime.
And the idea is to swallow the surgeon. I'm talking about very small machines.
Like the fantastic Voyage, scientists are diving into the unknown on the nanoscale, with many ethical and moral considerations that may arise from the use of this transformative technology and its limitless possibilities. One thing is certain: the smallest invention in human history will soon be the biggest.